All right, welcome back for part two. The first questions are basically just getting used to this log business. Here, we've got a power in exponential form, and we know that we're going to write this in log form. So the word log shows up somewhere. Where's the base? Well, the base is that little subscript. And then we know the answer is the exponent. So the answer is the x, and the big number, the power, is the inside. Dandy. Okay. So these two things are equivalent. When I see one, I can write the other if I choose. So here, when I think of the log, and what's the base? Log of base 2 of 32 equals 5. Right? There's the exponent. There's the base. These two things are equivalent. And as we'll see soon, what we can think of, if I wanted to change from one statement to the next statement, is I could almost think of taking the log base whatever of both sides. So for instance, here, let me just move this thing down a bit. If I take the log of both sides, and of course you can't do this, you're not writing this down. If I take the log base 2 of both sides, log base 2 of both sides, okay, there's that. But notice what happens here. Here I have a function, the log function, composed with its inverse, exponential function both base 2. It's almost like these two things, log base 2 and exponential function base 2, that's like f composed with f inverse. They annihilate each other, and I'm just left with 5. Now, I might be getting ahead of myself here, but that's what we're thinking. We're thinking this magic operation that's going to help us solve some equations we got stuck in last year and already this year is going to be this log business. And in fact, that's what's going to happen. For now, we're just getting used to this log thing. So let's not think too far ahead. Let's just enjoy how easy this is. Here, exponential form. The base this time is 7. The exponent is -3. That goes on the end. And the power, the answer, is on the inside. And notice, these are all true statements. These are true statements. And again, I could think of this as, all right, what's the exponent base 7 of this thing? Well, it's 7 to the exponent -3, and these two are equivalent statements. So now, if we wanted to write a log statement in exponential form, how does that work? Well, there's the base, right? And there's the exponent. There's the base, there's the exponent, and the inside is the power. It's like the answer in exponential form. In log form, the exponent is the answer. Well, that's different. So let's see the next one. Here we go. The base is 7. Right? The exponent is 2. Base is 7. Exponent is 2. And 49 is the power. That's pretty neat, but easy enough. What would be the operation that I was talking about there? Well, one thing I could do if I wanted to solve a log question is, instead of thinking of the opposite operation as log, what's the opposite operation of log? Well, it's exponential function base 7. And again, you don't have to write this down. I could raise both sides of the equation into the exponent 7. So 7 to the exponent whatever and 7 to the exponent whatever. On this side, notice I just get my 7 squared. But what do I have here? I've got exponential function base 7 and log function base 7 composed with each other. Again, I've set up this function composed with its inverse. These two annihilate each other, and I'm just left with 49. And again, I'm getting ahead of myself a little bit because these aren't that hard. Right? I'm kind of overthinking it, but you'll see where I'm going soon. What about this one? Here, the base is 3, the exponent is -3, and the power is 1/27. And of course, this is a true statement. If I wanted to solve this exponential statement, 3 to the exponent -3, well, I'd think of the negative exponent as 1/3 cubed is 27. Yep, that's a true statement. and that matches up with what we know about exponent rules. All right, let's keep going. So now, if we wanted to evaluate this statement, log base 3 of 81, notice one way I could do this is by saying, well, I don't know what this answer is, but let's change this to a more familiar form. I could change this to an exponential form, right? And I'm going to call this method 1, by the way. And this method 1 probably will move away from fairly quickly, maybe. We'll see. Base 3, right? So base 3, I don't know the answer, but I know that the power is 81, right? Well, what exponent base 3 gives me 81? And then this is actually something we solved in grade 11. I can think of 81. Well, 81 is just 3 to the exponent, guess and check a little bit here. It's 3 to the exponent 4, right? 3 times 3 times 3 times 3 is 81. And then I can see, okay, this must be x is equal to 3. This answer is, oh, sorry, not 3, it's 4. Is answer to 4. All right, dandy. That's one solution. I'm going to move this one over a little bit. Can I move this over? No, I can't. Let me just get in there and move that over a little bit. Yeah, I'm messing up my diagram. That's okay. Dandy. So I want to show you a different way to do this, and this is, I think, a nicer way. Here's method 2. And it's got to do with, let's set up a function composed with its inverse. If I can do this, I must be able to write this as a power of 3. This is going to be 3 to the exponent something, right? If I could fill in this box, then it's the answer because I have a function composed with its inverse. And the function composed with its inverse of box is just equal to box, right? So if I knew what that was, so this whole problem boils down to, how do I write this as a power of that? What's the exponent? And if I can do it without a calculator, or if it's actually works out, then it should be pretty straightforward what this is. A function composed with its inverse, the answer is 4. This is kind of a shorter, almost more clever method. So, and that's what we want to start moving to. By all means, if you like this method where we let this be equal to x and then change it to the exponential form so it looks more familiar, you're welcome to do that. So if I can do this, what I want to do is write the inside thing as 10 to the exponent something, right? Because I know the base is 10. The base is 10, the base is 10, the base is 10. So this inside thing, 1,000, is 10 to the exponent, well, this one's easy, right? 10 times 10 times 10, that's 10 to the exponent 3. And then function composed with its inverse, this answer is just 3. Right? You see that? Nice. Here we go. This is a lot harder, right? Because I want to write 81, or 82 rather, as 10 to the exponent something. Right? Well, hang on. 10 to the exponent 1 is 10. 10 to the exponent 2 is 100. What's box? Well, now I'm back to this stupid guess and check thing, right? It's going to be somewhere between 1 and 2, probably closer to 2, I could guess. Box is about equal to, I don't know, 1.8 maybe? Who knows? Guess and check. Sad face, right? We're still stuck. And in fact, you might be tempted to change this one to exponential form when you get stuck. And we get 10 to the exponent x is equal to 82. What's the exponent of 10? That gives us 82. And again, that leads to sad face. Well, just hang on a second. This log base 10 is actually a button on our calculator. And I'm getting my my graphing calculator fired up, although you will have a log button on any of your scientific calculators, and this is going to be good, clean fun. Watch this. Log 82. And we think it's going to be around 1.8, but let's just see. It's 1.9. Is about 1.9, and there were some more decimals where it was 1.91, about. And we knew it was going to be around there. But that was pretty good. Notice, I want to show you something here. There was no 10 in there. Notice that when the log button and it's hooked up with 10 to the exponent x is called the common log, is base 10. The common log is base 10, and so normally we wouldn't write in the base. If you see a log with no base, then it's base 10. Okay? Nice. All right, how do we do this one? Well, notice if I can somehow, and I'm thinking ahead here, if I can somehow write this as 2 to the exponent something, then the log base 2 and exponential function base 2 will wipe each other out, and then my answer is just whatever I fill in the box. But I recognize these things both as powers of 2, right? Because I remember my exponent rules from grade 11, and I did my preview work from before the trig test. So roots mean fractional exponents times 1/16. 1/16 is 2 to the exponent. There's a negative exponent here, right? If I actually put this in the denominator, I can think of this as, but 16 is 2 to the exponent 4, right? Well, that's 2 to the exponent minus 4 then. So 1/16 is 2 to the exponent minus 4. How do I deal with two exponents when I'm multiplying? Well, I add the exponents. Quickly in my head, how do I add a half and negative 4? That's 2 to the exponent negative 3.5, or 3.5. So now I've got what I wanted. The box is negative 3.5. Function composed with its inverse, negative 3.5. Done. And exact. And no button on the calculator needed. Dandy. All right, let's keep going. Notice what was the trick there? Why did I know that I couldn't do this? That I could do this one exactly? That I didn't need my calculator? Is I recognized that both of these expressions could be written as a power of 2, and then I could use my exponent rules. All right, how am I going to do this? Well, one thing I could think of is just change the form. You know, I could just change this to exponential form and have a look at it. So here's method 1, is to change this to exponential form. Well, the base is 3, right? The base is 3. The exponent is 5, because a logarithm is just an exponent, and that's x is the answer. So then all I have to do is put that into a calculator. 3 to the exponent 5, I believe, is 243. Right? I just put in 3 to the exponent 5, or this might be your exponent button. I don't know what the button on your calculator looks like. Is 243 rather. That's a bit messy. Oops, bit messy. Bit messy. Good. Method 2. And I like this method better because it feels more like equation solving we've done before. Is now I can think of what's the opposite operation of log base 3. Well, it's exponential function base 3. So to get rid of log base 3, I put in exponential function base 3 to both sides. Well, what I get on the right-hand side is 3 to the exponent 5. And on the left-hand side, I have a function composed with its inverse. These wipe each other out, and I'm just left with x, and I get the same answer. Great. All right, well, now let's think of this one that way. And by all means, you could do this by changing to exponential form. That would be fine as well. I could think of this as what's the opposite operation of log base 5 of both sides? Well, it's exponential function base x of both sides. All right, well, how do I manage that? Well, I take exponential function base x. A function is composed with its inverse here. I'm just left with 4 on the left-hand side. On the right-hand side, I'm left with, well, I'm left with x to the exponent minus 2. Now, how the heck do I solve that? Well, I'm going to do some exponent rules, right? Negative exponent means 1 over. If I wanted to solve this, cross multiply. and I get x equals positive and negative a half. Now, there's something, right, when I square root, there's something a little bit weird here. Log base x, base x is defined only if x is greater than 0. So for instance, and I don't know if you ever realized this, but if we had an exponential function, it was never -2 to the exponent x. We never ever had that, because what would happen, this function has got lots of holes all around it, because for instance, if I had x was a half, that's the square root of -2, which is not defined. So we say these functions are only defined if the base is greater than 0. So this is the base has to be greater than 0. We say that is not allowed. That's not allowed solution, inadmissible solution. Dandy, I am going to stop the video, and we're going to actually come back for the graphing example for the dreaded part 3 of the video, but we're still keeping these. Well, this one's getting a little long, but we're going to come back for part 3 of the intro to logs video.